Okay, so 11.5 is about a radioactive half-life. So we've already encountered half-lives in the context of first-order chemical reactions. And nuclear reactions also follow first-order kinetics. And so the half-life for a nuclear compound is the exact same as the half-life for a chemical compound. But let's show exactly what that means. The half-life is the amount of time that is required for the radioactive element to decay to half of its initial amount. And we could talk about this in terms of a concentration, or just a raw mass, or a number of moles. All of those things are proportional, so it doesn't really matter. If you wait one half-life, then you see on this graph that the fraction of the sample remaining will drop to 0.5. If you wait another half-life, it's down to 0.25, which is half of what it was after the first half-life. And then 0.125, and then 0.8, 0.0875, and so on. And so even though the actual rate of decay is dropping, the slope is becoming more shallow, and the amount that is lost at each step is smaller and smaller, but it still is perfectly rigidly constant that you'll reach half of the previous value after one half-life has elapsed. And so when we're dealing with first-order kinetics, we talked a little bit about integrated rate laws, I think, or maybe that's a 12-20 thing, actually. Anyway, when we went over kinetics and we talked about first order, second order, zeroth order, we never quite gave you this really neat equation. So here is the way to tell how much of a sample is remaining, even if you aren't at an even number of half-lives. So the fraction remaining is going to equal 0.5 raised to the nth power. N is the number of half-lives elapsed. Okay, the number of half-lives that have elapsed. So let's look at a table of half-lives, and we'll pick something out here, and we'll just make a good little problem. Okay, so if we look at this table, you see a number of radioactive isotopes or radioisotopes that are useful and common in the world around us. Their uses are shown on the far right, and in medical imaging and in what do they call it? Anyway, in cancer treatment, cancer therapy, these are common places where you'll encounter radioactive isotopes. Okay, and they have really different ranges of half-lives. Things that we use in radiometric dating will have half-lives on the order of thousands of years or even billions of years. And things that we want to use for scanning and tracing might be as short as 6.01 hours, like technetium-99 down there near the bottom. So let's look at cobalt-60. So cobalt-60 has a half-life of 5.271 years. Cobalt-60 is equal to 271. For cobalt-60, the half-life is equal to 5.271 years. I want to make sure I get that right. 5.271 years. And we could have chosen any one of these. Cobalt was just an interesting one for me. So let's do two types of problems. The first one would be to say how much is remaining after a certain period of time has elapsed. And so let's say you start with 10.0 grams of cobalt-60, and after 20 years, how much remains? After 20 years, how much remains? So what we would do is say, well, how many half-lives is 20 years? It's a little bit less than 4, but we better figure out what the actual number is. So we're going to take 20 divided by 5.271 and give it a second. Sorry, my calculator hadn't quite booted up. That's 3.79 half-lives. So n is equal to 3.79 half-lives. And so we'll take 0.5 raised to the power of 3.79, and that's going to be the fraction is going to be 0.07229. .07229 is the fraction that remains, so we'll multiply that by 10 grams to figure out how much remains. And that's going to be 0.723 grams remain. After 20 years, your 10 grams of cobalt-60 will have decayed until there is only 0.7 grams left. And then the other way you might want to solve this sort of a question is to say, how long will it take to reach a certain amount? And these are a little bit more tricky. So we'll say that the fraction is equal to 0.5 raised to the nth. And so we'll say again we've got 10.0 grams of 60 cobalt. And my question is, how long until only 8 grams remain? Okay, well, 8 grams as a fraction is 0.8. So 0.8 is equal to 0.5 raised to the nth power. That looks like a simple enough problem to solve, but how do we get the n down so that we can solve for it? We're going to have to take the natural log of both sides. So the natural log of this and the natural log of that. Well, now the natural log of an exponent can, this exponent can be brought out in front. Okay, that's something the mathematicians taught us. It's the reason why logs are so useful to us as a tool for solving problems. So what we get is that the natural log of 0.8 is equal to n times the natural log of 0.5. And now we can just divide natural log 0.5 over to the other side. So that n is equal to the natural log of 0.8 over the natural log of 0.5. And let's figure out what that is. Okay, that's going to be 0.322. Now that is 0.322 half-lives. Each half-life is 5.271 years, so we'll do 0.322 times 5.271. And it looks like that's 1.70 years. 5.271 years. What did I say it was? 1.70 years. So it'll take 1.70 years for 10 grams of cobalt-60 to decay down to 8 grams. So hopefully that made sense. And just putting this table of half-lives back up, you can see that if you have a half-life that's measured in terms of hours or days, the equation would be the same. Just make sure that you write the correct units of hours or days. This one was years. A lot of these are years. But the equation works the same. It's just your answer needs to be consistent with the unit of time that you use. Okay?